Welcome back. At some point, students learning oxidation reduction often ask, why does this matter? I'm never going to use redox anyway. Why learn this complicated way of looking at reactions? And it's a very legitimate question because redox, for all of its oxidation, reduction, while the electrons move from here to there, it doesn't necessarily make sense why this would practically matter. And the answer to this question, like where is this most useful to me day to day, could be shown by this reaction between the copper 2 ion and zinc metal. Now, I know it's been a long 4-day weekend. Let's take a break. Let's go back to the review. This is the loss of electrons. The number went from 0 to plus 2. Let me show you that really fast. So, is this oxidation reduction? That might be the last time I ask you that this year. But I want you to notice something. See, if this lost electrons and this gained electrons, then that means the electrons flow from here to here, right? That I have electrons moving physically from one chemical to another. And that has a special name. Let me draw you a picture really fast. I didn't promise it was going to be a good picture. So the zinc is losing its electrons, and the copper is taking the electrons from the zinc, right? It's kind of like a path or a river where they leave from here and they arrive here. But that's actually a really important concept. See, last week I showed you that you can get chemistry to happen by pushing electricity through it. But here's those same wires we used to do that. This could represent the thing that gives electrons off, and this red could represent the thing that takes electrons, because that's how I've got them set up right now. And that's how they're conventionally wired. And if I take these two things and I connect them, hey, will you look at that? Little sparks. Kind of cool. So, that is, by definition, electricity. Now, this isn't coming from any chemical reaction. This is coming from a wall power supply. This is just electricity. Which, if you really want to go down the road, yes, eventually at one point was a chemical reaction because my house is powered by coal burning. But let's not abstract it too much. This is just electricity. But that is just, these sparks here are just the flow of electrons from a source to a sink. So if I could set up a chemistry reaction where I had a source of electrons and something that was taking electrons, and I could put a wire between them to allow the electrons to travel physically from one thing to another, then I should be able to get electricity. This is a huge idea, and obviously we didn't work on it backwards. In real life, we discovered, wow, if you do these two things, it tingles, or it rusts faster, or whatever. But this is how we discover electricity, at least in terms of, current flowing electricity. Obviously, static electricity we've known about for as long as human beings have had, hair around them. So, for a while, in other words. But in terms of this flowing electricity, well, that is a bigger deal. So let's go over to Rockhurst, and something I filmed before this quarantine actually started, and let's build a basic battery. Let's start from there. All right, so I do need to make a salt bridge, and every year I seem to lose mine. Now I've got some straight glass tubing here, and that would work really well, but I need to put two bends into it, so it makes like a U shape. And obviously that means I'm going to need to bend this glass. Now, this is way, way, way more glass than I need, right? So I need to cut a piece first. And if you've never seen someone cut glass, there are lots of ways. And this is probably the worst way, but it will work well for what we're doing right now. So first thing I'm going to do is I'm going to light a Bunsen burner. And I'm just going to gently heat a spot on the glass. I'm not going to do it for very long. Now, normally you'd want to score and carefully crack. But for what we're doing right now, this should work just fine. So I've heated it. I'm just going to hit water straight on there, right? And nothing happened that time. So we're going to heat it a little longer. what we're trying to do is thermally stress the glass. Now, if this was being used for really important stuff, we wouldn't want to do it this way. But for what we're doing right now, it works well. And there you can see that nice crack form, right? So if I come in here with my hands, you can see I should be able to just easily break the glass off. Now, that's a very rough edge, right? What I'm going to do is I'm just going to tap it, break the loose glass off, and I'm going to fire polish that end. Oh, looks like I got another crack forming, no big deal. And now I'll clean it up. Super, super easy. I'll finish this up off screen. It's not particularly exciting, but in the end, I'll get a nice flat ring, and it will work well for what we're doing. Okay. All right, so the first thing I'm going to do is I'm going to make a bend, and that's going to involve me heating for a while until you see the yellow flying from the sodium in the glass getting excited, and then slowly letting it bend. I think I'll just speed this up so you can see what's happening, because it does take a little bit of time. All right, so you can see I've got a bend there, and it's not pretty, but it will work just beautifully. Now, if I just cool this right now, it will crack. I need to do what's called annealing. So I'm just going to gently heat it over the top of the flame and cool it off by slowly moving it farther and far away from the flame. I'm not going to show you that on video, though. It's really boring. All right, so our first bend is done, which means it's time to make bend number 2. By no means beautiful, but it will work just fine. So I just need to cool it gently again over the flame, and then we'll be good to go on the next part. All right, so we've got our completed salt bridge here, right? It's a U shape, and all the way through there's a hole, even if my glass bending is really ugly. And let's be very clear, this is very ugly. It will work. But it's not a salt bridge yet. Right now, it's just a piece of glass. And so to make it a salt bridge, I'm going to fill it with, well, water, but also some sodium sulfate, which you can see in the background. Now, obviously, our stock of sodium sulfate's a little old. That's not going to matter. But let's go ahead and prepare this really fast. I'll probably time-lapse this bit for you really quickly. So if you see, there's a lot of salt in the bottom of this, a lot. In this case, sodium sulfate. And I'm going to add some water to help that dissolve. So I'm going to fill that up real fast. And of course, water finds its own level, right? As I fill one side, it will level to the other. Great. That's basically a done salt bridge. I've got some cheesecloth here, some just cotton. And I'm going to stuff that cotton into each neck here to help kind of seal that liquid in. All right, and there we're really close to a completed salt bridge. I've got water and I've got these cotton stoppers, and this is ready to use to make a battery. So let me clean up this space and then we'll be right back. So let's actually make the battery. I've got some new chemicals over here. I've got some copper sulfate here, and it's in different hydration states. You know, down towards the bottom, it's closer to its pentahydrate. Up top, it's dehydrated some. Doesn't really matter. It's going to go in water. It'll work just fine for us. And I've got some zinc sulfate here, which is an old chemical, so much so that the side actually has an antidote on it, which I thought was kind of fun. Basically, give this chemical, drink some water, keep throwing up until it's clear, lay down, and then give, coffee and milk. So great, I don't have any of those things with me, so I'm going to avoid breathing the dust or eating this. So let's get a little zinc sulfate. And it doesn't need to be a lot, like that's plenty. And I'm going to add it over here to this beaker. And let's get him out of the way since he is a poison. Don't really want to deal with him. And then to the other side, I'm just going to add a little bit of copper sulfate here, just a nice spatula tip. All right, cool. So I've got my two chemicals here, and they're both basically ready to go. Give them a little bit of water, dissolve them. I'll probably speed this process up here for just a second. All right, so those are obviously not all the way dissolved, but they'll work just fine for what we're doing. Our next character here is going to be the salt bridge we prepared. So we'll carefully lower that in. And there we go. Maybe stretch these things out a little bit. And now that's the basis of our battery. Now, obviously, our battery needs more to it than just that. Obviously, right now, that's just two liquids connected by a third liquid. And for that, we're going to need a little bit of metal. I've got over here a sample of copper, which you can see I've scratched with some steel wool to make shinier. So we'll introduce the copper to the copper solution. And then I've got some zinc, or what I'm hoping is zinc at least. It feels like zinc. Could be aluminum. So I've got this zinc here, and I'm going to lower it in. That is now almost a battery. Electricity should flow from one side to another, and we can check that using a tool called a multimeter or a voltmeter. And it's not going to be beautiful, but you can see there are numbers there. And if I take these probes here, you can see them, and touch them to the metal, hey, they're numbers. Now, those numbers aren't huge, but there's something. Those numbers are in millivolts. So this is 1,040 millivolts, or 1.04 volts. This reaction should make 1.10 volt, but there we go. And if I wanted to see it kind of not in the millivolt, I could just change the range here really fast. And you can see it kind of in the more normal ranging. See if we can't get it to pop up there. Looks pretty like it should work. There we go. And yeah, peak, you're seeing that 1.1, 1.3 hold. Now, this isn't very useful. I can't extract a lot of power from this. And you can see the voltage is, well, about a volt. So I have an idea. I'll be right back. So let's actually pause for a second. What I want to do is look at these three batteries and take them apart a little bit and learn how they work. Yeah, I've done this before, but I want to show you why I did what I did at Rockhurst. I'm not really an engineer or a chemist, right? So it's probably good for me to look at what other chemists and engineers do when they build their batteries. Now, I'm going to be clear before I go into this. A couple things. One, obviously don't do this at home. Batteries contain normally strong bases. They're alkaline. And so if you're not being careful, you can get a chemical burn that way, especially in your eyes. I'm going to be wearing goggles and gloves in this. And two, the chemistry here is different than what I'm using at school. I was using zinc and copper at school. This is going to be based around zinc and manganese, or a few different chemicals in here are possible. But the difference is my battery at school can make about 1 volt, and this can make about 1.5 volts. And what we'll deal with next is learning how to actually do that. So without further ado, let's take these batteries apart. So welcome back to the bench. I have 3 different batteries here, a D battery, a 9 volt, and a 12 volt lantern battery. And at first glance, I chose these 3 for pretty much the most obvious reason that you can see here is they're very different. Some are nearly as large as my hand, and some are quite small. And that the correlation between voltage, which is kind of the amount of potential it has, isn't necessarily just a size thing. Something else has to be going on. So I thought we'd take a look inside these. That's why I've got these gloves on, and kind of show you how they work. I think we're going to kind of work from small to large, so we'll get this guy out of the way for the moment. And get ourselves into here. So I have an assortment of tools over here, and I can kind of see along the edge here. Yeah, it looks like there's a kind of a wrapper. So I'm going to go ahead and work on this. I'll probably speed it up for you for just a second, and let's go ahead and take a look underneath that wrapper. True story, this knife has been to like 50 countries. It's one of my favorite, and it's super, super cheap and super easy to use. Alright, so I've scraped a bit of this off now, and you can see that it's a metal all the way around, and it's got a pretty thick case to it. Along the bottom, there's clearly like a cap here, that's been crimped on. If I get the knife in there and I wedge it, and I work around the edge slowly, there we go. That cap comes off. Okay, and then within that, there's a little, like, it looks like a nail to me right here, so let's kind of pull on that. And then get a hold of it with pliers. And it got really loud here in terms of I hit the desk card, so I'm just going to voice it over for a second. As I pull this nail out, you'll notice that the inside of the battery leaks out, and I went ahead and dropped it. Caught me by surprise. Normally it's a little slower than that. Not every battery will do this, and obviously that's why you don't want to take these things apart. So that chemical there is caustic or alkaline. That's why these batteries have their name. Even though this battery was dead, that stuff is still not pleasant to get on your skin or on other items. That being said, as long as you know it's coming, it's not so bad. So coming into here now on the top, you can see if I peel it back, it's just a metal case. So this whole metal from here to here to here, wrapping around the whole thing, was defined as plus, and then just that little nail sticking out the bottom like this was a minus. So we had our two pieces that were apart from each other and not electrically making contact. I can show you that by wiping off here, and you can actually see the plastic here that insulates this rod from touching the outer case. So the construction of the two is going to be this minus is separate from what's the plus, and so whatever's packed on the inside must be completing the circuit, the electrochemical cell from the outer wall to the inner wall. Alright, so this one will be a little less exciting, to be honest. Another dead battery. I just pulled it out of a smoke alarm, I don't know, a week ago. It's a 9-volt battery, and again, I want to do kind of the same process. I want to see kind of what's going on right under the wrapper and then get to the inside. So let's go back to the time lapse to watch the wrapper come off here. Okay, just like before, you can see there's a metal case, which is kind of obvious from here, underneath the wrapper. And this wrapper is a little hard to get off, but that doesn't really matter. Looking in, there's a pretty clear seam here along the side, so we might have an attack vector where we can just come in with a pry and hit it open. We also might be able to get in by taking the top off. I think I'm going to go down the side just because it might be more interesting. So let's go ahead and do that. Alright, so it looks like we've probably made our way in. We've broken open that little seal. And from here, I should be able to just slowly peel away the metal, and I can. And this might surprise you. See, inside, there isn't one, but rather 6 batteries. And there are these little plates as well. Alright, so let's look what you actually got out of this battery. So there's the case itself, which has got a very interestingly gold interior, and obviously no one ever sees the inside of this metal, at least unless they like hit it open and cut it open with a knife. So there must be some purpose to that, and the case, unlike in the 1.5 volt battery we had here, the case doesn't really do a lot. As a matter of fact, this gold coating here is going to be kind of like a Kapton, something to make this insulated, that it's not conductive across here. We've got these 2 pieces of cardboard with some metal strips on them, the contact you're familiar with, and then 6 little batteries. Now, each of these batteries is wrapped in this pink tape. The tape is not particularly strong. It's just barely on the surface, right? Much easier to get off than the wrapper. And that tape is protecting the outside so that it's not live to the others, right? Because if these were all things were all packed, static. We're all packed inside, and if they were touching each other, they'd short. And so they have to put tape around them so they wouldn't short. So this is part of the battery. This is live. This is the minus here. And then in the middle is a little knob, just like before. And just like before, if we pull on it, we would find a little nail, a little, what we're going to call electrode. Now, bearing the reminder that this has an alkaline, somewhat caustic substance in it, never something to really try doing at home. With that out of the way, we're going to open this up at home. Okay, back to time lapse. And there we go. You can see inside there's some kind of goopy white powder, the same as in the 1.5 volt cell here. And then a small metal electrode. And if I get this in the right spot and get this thing to focus, which, yeah, you can see that. You can see it's actually a little corroded in there. That's like, looks almost rusted. Well, the neat thing about this battery is inside of a 9 volt battery are basically 6 little versions of this. And a D and a C and an A and a double A and a triple A and a quadruple A, such a thing exists. They're all basically the same battery. See, there's no chemical reaction that gives enough power to make a 9 volt system all at once. So I got to stack up different little chemical reactions to get that. Now, there's a trade-off. This battery has a lot more chemicals in it than this one. So for 1.5 volts, this one's going to last a lot longer than this little tiny battery, right? But that's okay because I don't need this to last as long. I need it to work together in a group of 6 to give me 9 volts. This can only give me 1.5 volts. And the amount of chemistry in this and the amount of chemistry in these isn't that different. All right, let's go ahead and clean up the spot for just a second, and then I will be back to you. All right, so I've got this big battery, and the idea is you can use it to power something that takes a lot of electricity for a long time, like a lantern. And the battery's so kind of intended for like long-term use that you can see it's actually got like a screw terminal to clamp onto instead of just like putting it into a spring. Now, I've already popped this one open, so we can kind of take a look inside. And it probably at this point shouldn't come as a surprise to you, but maybe it does, that all that's in here are 8 of these. All the same. This cell here is just wired so they add up. Now I said this was 1.5, right? 1.53, 6, 9, hey, 12. 12 volts. So something about the 9 volt battery, because remember, the 9 volt battery had something in it. It had 6 of these. Well, 1.53, 4.56, 7.59. So all of these things are built up of the exact same chemistry that gives 1.5 volts per reaction. And that's not surprising. The chemistry is the same. If I were to come into here, I would find the exact same stuff. Now, I don't want to take this one apart for 2 reasons. One, it's the only one I have right now. And 2, it's got a little corrosion stuff in here. It's just going to be a mess. You already know what it looks like. You already know it's going to spew a little bit of hydroxide out. Whatever. So, with that, we need to understand a little bit more. Because, see, I see that if I have a crappy battery, and I just stack lots of them together, maybe I can do something else, which gives me an idea. Let's go back to the lab. All right, so it kind of looks like a science fair project, because it kind of is. I just built 4 of them, and I just used salt bridges made of paper towels, and you can kind of see how I built it really fast in this time lapse. All right, so what's happening here is each output of the circuit is feeding into the next one's input, something called a series connection. And so I just have 4 batteries, and remember each one of these is supposed to be about 1 volt. So we would expect about 4 volts, and instead it was like 1.06, so let's call it like 4.25. You'd expect this thing to give a little more voltage, a little more potential. So really quickly, let me set you down. All right, so not ideal, but it will work. And what I'm going to do is I'm going to take this probe here and connect it to the minus, and then take the other probe here
and connect it to the plus. And there we go. Our battery's working. We're getting 4 volts. That's kind of exciting, actually. I mean, it's a big messy thing, but it shows that's a battery. That's a real battery now. I have a single measly little LED here. And my colors are backwards on these. I'm not going to be bothered to fix it. So let's hook the LED up backwards here real fast. So I've got one terminal connected, and then I'm going to connect the other. And if you look really carefully, it's glowing. I mean, it's not, that's pretty lame, but it is glowing. Maybe, 1 second, I have an idea. Hold on. Yeah. There we go. I mean, yeah, that's not very useful, to be honest. To be honest, that's actually pretty worthless. You need so many of these batteries to make a functioning actual battery. But you know, it's at least it's lighting the light up, right? Now, what I think is so neat about this is the fact this is actually getting electricity straight from the reaction. That the fact this light is on right now is only a result of electrons moving between copper and zinc. That's actually the redox in redox happening. Now, I think that's where I want to end this experiment. Let's go over and look at a picture really fast.
So this, believe it or not, is what's inside a normal laptop battery, at least a slightly older one. More modern laptop batteries are flatter. They're a kind of a flatter cell. These are different than the ones I took apart. The ones I took apart were one-use alkaline batteries. These are rechargeable lithium ions. The chemistry going on in these little orange cells is very different. But you can still see that we're packing more small batteries together to act at a higher voltage, to act like a bigger battery. And that's a really common practice. This is what's inside like a power tool battery, like a drill. And you can see again that these lithium ion cells that are stacking up to make a larger voltage. In this case, it's not only stacked up, it's probably in parallel and series. That's beyond the point. These batteries, if you were to cut them open, would catch on fire spontaneously or even pop in a little explosion. They're quite dangerous to puncture. That's why you put a big, heavy plastic case around them so you can't stab them. And it's why taking these kinds of batteries apart would be way too dangerous to do inside. And it's why I really implore you, again, don't actually do that. And here's something where a ton of these batteries have been welded together on little strips to build a giant battery. It's weird to think that something would need that much battery power, but I can show you what those are used in here in just a second. And actually, that's just one small part of this. You need hundreds of those stacks together, and you get this battery, which is what's underneath a Tesla. But I think it's kind of neat to see that the same concept of my little copper and zinc batteries, which is this one little chemical reaction that you just kept repeating and wiring together in a certain way, builds up enough electricity to do, well, this. I mean, I could barely turn on a light, and this person's driving around a car doing a burnout on effectively the electrons going from, well, one metal to another in an oxidation reduction reaction. And all electricity that's not plugged into the wall in your life, I don't care if it's your phone, your computer, your whatever, as long as it's not got a cord, is coming from a chemical reaction just like this, and probably several of them stacked together. So the goal of today was to quickly show you the inside of a battery and understand how they work at a high level. And what we'll do next time we meet is we'll come in and look a little bit more at it as a chemist would and understand, well, how do they fit together and why does this work? So until then, buen camino.